Is it a unit cell? I give you 10 seconds to think about it. Is it a unit cell? Blue triangle. The answer is no. Why no? Okay, so the next one is like this, right? Okay, for the blue triangle, I change it to blue color. The next one like this. You may say the same one. There are many triangle ones, but have you noticed that this, the number one triangle and number two triangle, they have different orientation. One is triangle, the opposite triangle pointing down, and number two, the triangle is pointing up. So triangle one and triangle two have different environment. Okay, so the unit cell must always be the Bravais lattice. So this triangle is not a Bravais lattice, and therefore it cannot be chosen as a unit cell. So for this case, you have two choices to choose the unit cell. You can pick the green square unit cell, or you can pick the red parallelipiped unit cell. Okay, but definitely not the blue triangle unit cell because it is not a Bravais lattice. So for the primitive and non-primitive, primitive unit cell is the unit cell with the smallest area which produce the coverage. Smallest area means that there's only one lattice point, one basis. Okay, so in the two-dimensional case, the area of the unit cell is given by S equal to A cross product with B. Okay, doesn't matter, you know this. So the choice of the unit cell is not unique and is detected by convenience. Okay, whenever convenient, then we can choose this as the unit cell like what I showed just now. For a primitive, we have different choices. And then for the unit cell, the definition for the unit cell can be primitive and also non-primitive. So for this case, you can see that the green one is the non-primitive and the red one is the primitive. Doesn't matter, okay? So you can choose it as a primitive or non-primitive. And the unit cell discussed above is a primitive, okay? So the red one is a primitive and the green one is not primitive. However, in some cases, it's more convenient to deal with the unit cell which is larger. However, it exhibits the symmetry of the lattice more clearly. So for this example, if the green one exhibits the clearer symmetry, then we choose the green one. If the red one can show the better symmetry, then we choose the red one. Okay, then you may question, what is symmetry? Don't worry, don't panic. I will go into the detail of symmetry in the next chapter, chapter 2. Okay, so I will explain later on what is symmetry. Okay, so now I give the example. The vector A1 and A2 can be chosen as a primitive translation vector for the lattice shown in the figure below. In this case, the unit cell is parallelepiped. However, the lattice can also be regarded as adjacent rectangles, where the vectors C1 and C2 can be considered as translation vector. The unit cell in this case is larger. So in the first case, the parallelogram one, there's only one atom in the unit cell or one lattice point or one basis, whereas in the second case, there's a lattice with a basis, okay, two atoms. And then there's also two basics. Two basics doesn't mean two kind of basics, it's different thing. Two kind of basics mean that, okay, let's say two kind of basics means that the first basis is H2O, the second basis is CO2. Two basics mean that there are two H2O. two basics with the same kind. Okay, so there are two basic for this case and two lattice point. So this basics consists of two atoms, one located at the corner, y corner equal to 1 because 1 over 4 times 4 equal to 1. Then the other one at the center one contribute 100% to this unit cell, so equal to 1, so 1 plus 1 equal to 2. So the area of the conventional unit cell is larger by the factor of 2 than the area of the primitive cell. So the area for this unit cell is double the area of this unit cell. Okay, so for this type of the arrangement, means something like this. You have two choices. The first choice is that you can take this, okay, and then this is the unit vector C1, C2, C1, C2, and then for this case, there are two basic in the structure. There are two lattice point, okay, and then there are also another option, alternative choice. We can pick this as the unit cell, okay. If you pick this as the unit cell, or you also can pick this as a new cell. Okay, doesn't matter. This one also can be unit cell. If you pick this as the unit cell, then now it only have one lattice point and one basic. So the three-dimensional parapiped primitive cell has the lattice point at each corner. So each lattice point is shared by 8 other primitive cells. Therefore, the total lattice point in the primitive cell is 1, where is 8 times 1 over 8 equal to 1. 8 because there are 8, the 8 is the number of lattice point for one primitive cell. You can imagine for one cube there will be 8 corner. You just, if you don't believe, you just take out any material that have the cubic shape, you can count there are 8 corner. Okay, so each corner have one lattice point, and that particular lattice point is shared with the other 8 unit cell. Therefore, you have 8 corner lattice point times the contribution for each lattice point is only 1 over 8, because that particular corner lattice point is shared with another 8. So 8 times 1 over 8 equal to 1. So for the primitive cell, the total lattice point is 1. So the volume of the parapiped primitive cell is V equal to A cross product with B dot product with C. Okay, A, B, C are the unit vector for the primitive cell. Okay, so this is simple cubic. This is body center cubic. This is face center cubic. Okay, for simple cubic, you can see that the contribution for this corner atom is only 1 over 8, and there are 8 atoms